You've probably complained about a car left running in a driveway. Wasteful. Pointless. Just shut it off. But have you ever stood at a working harbor and watched a container ship, the length of 4 city blocks, sitting completely still at the dock, engines audibly running, going absolutely nowhere? Why does a parked ship need its engine on? Is anyone even paying attention? Isn't this exactly the kind of thing someone should have fixed by now? The answer is not negligence. It is not laziness. It is not some outdated habit that nobody bothered to question. It's a machine so large, so thermally complex, and so chemically specific that the word off carries consequences most people have never been asked to imagine. And once you understand what's actually happening inside that hull, you'll never look at a harbor the same way again. Here's where it starts. The engine, at the heart of a modern ultra-large container ship, is not an engine in any sense you've encountered before. It doesn't sit under a hood. It doesn't share a building with anything else. It is the building. The Wärtsilä stands 44 feet high, runs 89 feet long, and weighs over 2,300 tons. Sulzer RTA-96C, one of the most common propulsion engines in deep water freight. It produces 109,000 horsepower. For context, that's roughly 1,000 family cars firing simultaneously, all of that force channeled into turning a single propeller shaft. Most people hear those numbers and let them pass. Don't let them pass. Because here's the thing that changes everything. That engine is not a mechanical device that happens to run hot. It is a thermal system that happens to move a ship. That distinction sounds subtle. It isn't. It's the reason the engine is still running right now, tied to a dock, going nowhere. A car engine is designed around a specific assumption. It will be shut off. It will go cold. It will be restarted tomorrow morning, and the morning after that. Every component, every seal, every tolerance in that engine is engineered around the cycle of on, off, on, off. Your car does it fine. A 2-stroke low-speed marine diesel is engineered around the exact opposite assumption. It is built to run, not to cycle, not to restart. To run continuously at operating temperature for weeks and months without interruption. Shutting it off isn't a rest. It's a disruption the entire system has to recover from. And recovery on an engine this size is neither quick, nor cheap, nor simple. This isn't a design flaw. It isn't an oversight from an earlier era of engineering that nobody updated. It's a deliberate architectural choice made around the physics of the machine itself. To understand why, you have to understand what heat actually does to steel at this scale. And that's where the real story begins. Getting a cold marine diesel to operating temperature doesn't take minutes. It takes 24 to 36 hours. Not because engineers are being cautious, because the physics of the material itself demands it. The entire engine block must reach 80 degrees Celsius, 176 degrees Fahrenheit, before a single combustion event begins. That heat doesn't come from firing the engine up and letting it warm naturally. It comes from steam lines and electric jacket water heaters wrapped carefully around the block, coaxing the temperature upward at a controlled rate, section by section over 1.5 days. Here's why that window isn't negotiable. The cylinder liners inside a marine diesel are massive steel components, machined to tolerances measured in fractions of a millimeter. When steel heats up, it expands. That expansion is not a problem. It's accounted for. The clearances between every moving part are calculated precisely around it. But that math only holds under one specific condition. The entire engine must heat together, gradually, uniformly. Push heat into one section faster than another, and the expansion becomes uneven. Components engineered to fit within a fraction of a millimeter of clearance suddenly don't fit at all. The result isn't a warning light. It isn't a fault code you clear with a diagnostic tool. The result is a cracked cylinder liner, or a piston seizure. A piston expanding past its tolerances and locking solid inside the cylinder. On an engine this size, that isn't a roadside problem. That's a dry dock event. The ship is pulled from service. Repairs take weeks. The damage bill runs into the millions before a single tool has been picked up. And that's before counting the lost charter revenue accumulating every day. The vessel sits idle. One cold start forced too quickly can produce exactly that outcome. So the engine doesn't go cold. Ever. In port, it throttles back, running at low power, consuming less fuel, but never allowed to drop below the temperature the system needs to function. The idle isn't waste. It's the cheapest possible alternative to a catastrophic repair. The physics problem is real, but there's a second reason the engine stays running, and in some ways it's harder to work around than cracked liners or seized pistons. It's chemical, and it starts with the fuel itself. Heavy fuel oil, the standard propulsion fuel for ocean-going vessels, is not fuel in any way most people picture fuel. It isn't refined, filtered, and optimized like gasoline or diesel. It is the residue left after refineries have already extracted everything more valuable. Gasoline gone, diesel gone, jet fuel gone, kerosene gone. What remains is thick, dark, and at room temperature closer in consistency to asphalt than to anything designed to flow through a pipe. It doesn't pour. It doesn't pump. Left alone at ambient temperature, it simply sits there, dense and immovable. To move through the fuel lines at all, heavy fuel oil must be heated to 135 degrees Celsius. Not warm, not hot. 135 degrees maintained continuously throughout every pump, every filter, every line in the delivery system. Which means the entire fuel infrastructure running the length of the ship is itself a heated network, kept alive by systems drawing energy from the engine. The engine heats the fuel. The fuel runs the engine. The moment that loop breaks, everything downstream breaks with it. If the engine stops and the heating stops, the heavy fuel oil begins to cool. Within hours, it thickens past the point where any pump can move it. Within a day or two, it doesn't just slow down. It solidifies. It becomes a tar-like sludge packed into every line and fitting throughout a fuel system, spanning a vessel that may be a quarter-mile long. Marine engineers have a name for what happens next. They call it bricking the ship. Not a metaphor. A precise description of a vessel rendered completely immobile, not by mechanical failure, but by chemistry. Clearing a bricked fuel system means applying heating equipment manually, section by section, through pipework running the entire length of the hull. The labor takes days. Port fees accumulate. Lost charter revenue runs at $150,000 per day. One cold stop in the wrong conditions can cost more than the cargo the ship was carrying. So the main engine stays running. But even when the main propulsion engine does stop for scheduled maintenance or a legitimate technical reason, the ship doesn't go dark. It doesn't go quiet. It stays completely alive through a separate set of machines that almost nobody thinks about when they picture a vessel at anchor. Every large container ship carries auxiliary diesel generators, smaller than the main engine, purpose-built for port operations and never off. They run the navigation systems, the communications equipment, the electrical grid threaded through the entire hull. But the reason they cannot stop isn't crew comfort or navigation upkeep. It's what's sitting in the cargo hold. A modern ultra-large container ship can carry 10,000 individual shipping containers. A significant number of those are reefers. Refrigerated units holding temperature-sensitive cargo that cannot drift from its target range without destroying everything inside. The strawberries from Chile loaded 3 days ago. The insulin manufactured in Germany bound for a distribution hub on the other side of the world. The flu vaccines headed for a West African port with no cold storage backup waiting on shore. Every single one of those containers is plugged directly into the ship's electrical grid, drawing power continuously, kept alive only because the generators are running. Shut the generators down and the reefers go dark. The temperature climbs. The cargo dies. The financial loss is immediate and total. And in the case of medicines and vaccines, the consequences extend well beyond a balance sheet into outcomes that are genuinely difficult to put a number on. Then there are the hydraulic systems. Steering on a vessel this size isn't a wheel connected to a rudder by a cable. It's a hydraulic system powerful enough to move a rudder blade the size of a suburban house. The ballast pumps stabilizing the ship as thousands of tons of cargo load and unload. Hydraulic too. None of it functions without continuous power. None of it stops needing power simply because the ship is tied to a dock. A solution exists for exactly this problem. It's called cold ironing, or shore power. A portside electrical connection that lets a vessel plug into the local grid instead of burning its own fuel at anchor. Where it exists, it works. Emissions drop, noise drops. The mechanical wear on generators running far beyond their design duty cycle slows. Fuel costs at port fall significantly. It is genuinely the right answer to the problem, and nobody in the industry seriously disputes that. But cold ironing requires infrastructure, high-voltage shoreside connections, compatible systems aboard the vessel, port facilities built or expensively retrofitted to support the electrical load of a ship that at anchor is still consuming power at industrial scale. And the global merchant fleet contains more than 50,000 active vessels. The ports equipped with full cold ironing capability represent a small fraction of the stops those ships actually make. For most vessels, on most routes, at most ports of call, the connection simply doesn't exist. The generators run, the fuel heaters run, the reefers hold temperature. The ship stays alive the only way available to it. Here's where the history matters. Because this situation didn't emerge from carelessness or indifference. It emerged from an economic decision made decades ago that was so logical at the time it became invisible. Heavy fuel oil became the dominant marine fuel after the Second World War for a single reason. It was cheap. The bottom of the refinery barrel, the residue nobody else wanted, was offloaded to shipping companies at prices that made ocean freight economically viable at the scale the post-war world required. The trade-off was everything described above: the viscosity, the heating requirements, the catastrophic consequences of a cold system. And the engineers of that era managed fuel temperature by hand, with manual checks and analog gauges, building habits and procedures that calcified over decades into ship design standards, into port infrastructure expectations, into the architecture of global supply chains that now move 90% of everything the world consumes. The system wasn't designed to turn off. It was designed to never have to. So the next time you stand at a harbor and hear that low diesel hum rolling off a ship that isn't moving, you're not hearing waste. You're hearing consequence management at industrial scale. That vessel is holding temperature on vaccines, keeping strawberries alive from a farm in Chile, running hydraulics on a rudder the size of a house. The cold chain that stocked your fridge this morning depends on it. The infrastructure is slowly changing. Shore power is expanding. Better solutions exist. But 50,000 ships aren't waiting for the world to catch up. The engine stays on, because off is a problem nobody has fully solved yet.